1 second.
Ah, there it goes. Okay.
Yes, now you're ready to go.
Great. So I guess welcome everyone to the construction section. So this section will have 6 talks. So we'll do the usual business. So 5 minutes for the talk, 5 minutes for questions. If you have questions, please feel free to post either on Zoom chat or on Zulip. So both me and Mariana, my co-host for the session, will be monitoring for questions. So without further ado, let's begin with the first talk. So the first talk in this section will be New Techniques for Traitor Tracing, Size n to the 1/3 and More from Pairings by Mark Zandri. And Mark will give the talk.
Thank you for the introduction. Right, so what is traitor tracing? The setting is we have a content distributor who is sending an encrypted broadcast to a bunch of users. And we're worried that some of the users will take their secret key and release it publicly or sell it to a friend or whatever. And the goal is to, if the content distributor ever finds such a leaked secret key, to identify the traitor. And we want to do this even if the secret key is embedded in a decoder program or actually even a physical decoder device, even if arbitrarily many users collude to build the decoder device, and even if the decoder fails most of the time. The main objective in traitor tracing has been to achieve traitor tracing with the best possible parameter sizes in terms of the number of users. So the relevant parameter sizes are the public key size, the secret key size, and the ciphertext size. What's known is, well, there's some combinatorial constructions just based on generic public key encryption, or you can do a little better based on identity-based encryption. There's a trivial construction where you just encrypt to every user separately. This has linear size, ciphertext, and public keys. And then there was an improvement using something called fingerprinting codes, which achieves constant size ciphertext, but at the cost of very large public keys and secret keys. And then there are a number of algebraic constructions. Maybe the most relevant for today is the pairings-based construction of Bonet, Sci-Hi, and Waters, which achieves square root and public keys and ciphertext. And then there were some more recent constructions using other algebraic tools that achieve all parameters constant size. In this talk, I'll focus mostly on pairings and weaker objects. And in this work, what we do is we develop a handful of new techniques for traitor tracing that gives new parameter size trade-offs for pairings and other primitives. For pairings, we achieve a variety of parameter sizes in the setting where the product of the public key, secret key, and ciphertext size is equal to n. So the Bonet, Sci, and Water scheme lies in this space, as well as the trivial scheme when instantiated from IBE. And that was basically it. And what we do in this work is we fill in this space a lot more. Perhaps the most interesting points here are the spot in the center where all public key, secret key, and ciphertext size are cube root n. And on the bottom left-hand corner where we get to constant size public keys and ciphertext, albeit linear size secret keys. We give a few other results. We consider the case of traitor tracing when combined with a broadcast functionality. And in particular, we give the first construction from standard assumptions with constant size ciphertext. And we also look at the combinatorial setting based on public key encryption or identity-based encryption. And we show how to achieve all parameters sublinear, namely n to the 2/3 based on generic identity-based encryption. So we achieved these results through a number of new techniques. There's this concept called threshold tracing, where you can only trace decoders that work most of the time. And we show how to actually generically remove such a limitation without asymptotically changing the parameter sizes. We show a general technique for trading off between public key and secret key sizes by reducing those at the cost of increasing ciphertext. We consider something called risky tracing, show how to, which is another weakening of traitor tracing. We show how to eliminate this weakening at the cost of larger secret keys. We show a way to convert something called threshold broadcast into traitor tracing, and we give a number of new algebraic instantiations from pairings. So that's the end of my summary.
Great. So thanks, Mark. So do we have any questions? So if you have questions, again, please type either in the Zoom chat or on Zulip. So I guess I can start with a question. So do your techniques generalize to settings like broadcast and trace, where we both have sublinear ciphertext as well as the traitor tracing functionality?
Yes, they all will the first four on this page are all generic, and they also apply to the broadcast and trace setting, and this is how we get our broadcast and trace results. The new algebraic instantiations, it depends on sort of what some of the instantiations will achieve the broadcast functionality, and others won't.
Cool. So how do the parameters compare in terms with respect to existing broadcast and trace schemes, say from Pairings? Or from
let me go back. Basically, if you're willing to assume things like obfuscation or slightly weaker primitives, but nonetheless non-standard, you can get constant size parameters for broadcast and trace. If you are focusing on standard assumptions, there's the old work by Bonnet and Waters, where just based on pairings, you can get n to the 1/2 for all 3 parameter sizes. We basically improve that down by getting constant size secret keys while maintaining the n to the 1/2 public keys in ciphertext. And then there was a more recent work by Goyal et al. That combines pairings with LWE to get smaller ciphertext. They were unable to get constant size, but they could get any arbitrarily small polynomial size ciphertext, but at the cost of at least linear secret keys and at the cost of at least linear public keys and quadratic secret keys. And what we're able to do is go all the way down to constant size ciphertext and keep the public keys and secret keys the most linear.
Great, thanks. So do we have other questions for Mark? I guess if not, then we can move on.
No, I think we don't see any other questions. So do we have an author to present the second paper, which is new constructions of hinting PRGs, one-way functions with encryption and more? Any volunteer to present the paper? Oh, we do have an author. We've been asking for the author to step in for a while. Okay, so this is our second paper of the session. And I guess the author presenting the paper is Satya Narayana. The floor is yours.
Thanks for the introduction. Hi, all. My name is Satya. Today I'm going to discuss about our paper on new constructions of hinting PRGs, one-way functions with encryption, and more. This is a joint work with Rishabh Goel and Brent Waters. Let's start with a brief history. Way back in 2017, Joe and others came up with this beautiful primitive called laconic oblivious transfer to make oblivious transfer more communication efficient. Later on, they used really cool techniques in this laconic OT paper. Later on, Dotling and Gerg abstracted out these techniques into a beautiful primitive called Kemenian hash with encryption. Later on, this primitive and its variants found tons of applications like identity-based encryption, registration-based encryption, trapdoor functions, designated verified zero knowledge, CPA to CCA transformation, trapdoor hash functions, and so on. That's a ton of applications. As it turns out, all these applications are based on a very few related primitives, such as one-way function with encryption, hash with encryption, hinting PRGs, and so on. These primitives are syntactically pretty related to each other, and some of them are even known to imply each other. And since these primitives are so powerful, like we certainly need more and more efficient schemes to build these primitives. And that's exactly what we do in this work. We build better primitives for better constructions for one-way function with encryption and hinting PRGs. Even though we concentrate only on these two primitives, we believe our techniques are helpful to build even other primitives as well. Let's see what one-way function with encryption actually is. As the title says, there is a one-way function component to it. So there is a function f that takes input x and outputs a value y. and there is an encryption component as well. So there is an encryptor that encrypts a message, and there is a decryptor that decrypts a ciphertext. But what are keys to these algorithms? The keys actually come from the one-way function part. Here, y acts as an encryption key and x acts as a decryption key. In addition to that, encryption algorithm also takes an index I and a bit B also as input. And now the decryption algorithm works if x is a preimage of y and if ith bit of x is equals to b. So not every preimage of y works for decryption, only specific preimages of y work. For the security part, first of all, f has to be one way. And secondly, f has to be smooth, which means if x is sampled from a uniform distribution, then the resulting y also should resemble uniform distribution. For the security of encryption part, if the adversary doesn't have the right decryption key, then the ciphertext should look uniform. Dotting and Gerg came up with a beautiful construction of this one-way function with encryption as well. Without going into further details of the construction, all you need to know is if you want to encrypt a message with respect to index I, bit B, and randomness row, the ciphertext is going to contain these elements. Here, n is the input length of one-way function. The ciphertext contains two n elements except for one block. The block that is opposite to I, bth index, that was missing. The security of the encryption scheme crucially relies on the fact that the ciphertext is missing in one block. And that's why we call it as missing block framework. Remember this picture of a slide ago? There are tons of applications in the literature, and all of them are based on a very few related primitives. As it turns out, the constructions of all these primitives also rely on missing block framework. So that's a very powerful technique. But the problem here is this technique is resulting in long ciphertexts. And if you use this one-way function with encryption to build trapdoor functions, then you're going to get long public keys. It tends to look out for new techniques and new frameworks to build these primitives. And that's why we introduce a new technique to build one-way function with encryption. And we also extend the same technique to constructing hinting PRGs. Now let's compare the efficiency of our work with that of previous works. The previous work based on dotting is dotting and Gerg, which is based on DDH assumption. That has the following time complexities. Our first construction is based on factoring assumption. As you know, we want to optimize encryption time and ciphertext size, and we want to deviate from this missing block framework. And so here are the time complexities. The rest of the complexities remaining the same are encryption time and ciphertext size are asymptotically better, and rest of the complexities are the same. We also extended the same techniques based on DBDH assumption, which is some pairing-based assumption. Even here, we optimize encryption time and ciphertext size to be asymptotically better, but the setup time, one-way function time, and decryption time are actually worse. So there is some trade-off here. Even in factoring-based assumption, our group sizes are bigger generally because the RSA modulus is bigger. So there is some trade-off there as well. Let's finally move on to a construction from factoring-based assumption. Here, the public parameters would consist of an RSA modulus n, which is a product of two large primes, and it consists of a generator G, which is randomly sampled from group Z and star, and it consists of two n random large primes, where n is input length of one-way function. And if you have input x, and if you want to compute one-way function on input x, then from each column of this matrix, you take one element depending on the bits of x, and you multiply them. So that's product of ejxj, and you raise it to generator G. And that's the output value of one-way function. And now if you want to encrypt a message with respect to encryption key y, randomness row, index I, and bit b, and this is how a ciphertext is going to look like. Remember earlier in the DDH construction, we had these 2n elements and we were missing in one block. And here is exactly the opposite. We only give out one block and miss out rest of the blocks. And that's where our efficiency kicks in. And that's where our encryption time is lower and the ciphertext size is also better. We also used really cool techniques and math theorems like prime number theorem for proving the security of this construction. You can have more details in the paper. Let me finally conclude the talk. In this talk, we discussed about one-way function with encryption, and we saw that the previous constructions are using missing block framework, and we came up with some better framework for constructing one-way function with encryption with shorter ciphertext size. And we also extend the same techniques for constructing hinting PRGs with shorter public parameters. We coded up all our schemes and evaluated the performance as well. You can find the details in the paper. For more details, you can look at the ePrint version of the paper and our YouTube talk.
Thank you. So we have some questions. The first question is from Mike Rusulek, who is interested to know how wild is this DBDHI assumption? Is it a Q-type assumption? Is it interactive?
It's a Q-type assumption. It's not interactive. The assumption states that if you have G power alpha, if you're given G power alpha square, G power alpha power n, and so on up to G power alpha power n, then you will not be able to compute E of G comma G power 1 by alpha power 1 by alpha.
Thank you. And this another question from Pratish. How is your views on using your techniques to build the same primitives from LPN or LWE assumptions?
Actually, I don't know much about that.
Okay, I think that's okay. It sounds like interesting future work. Any other questions? Do we have anything from the chat?
I don't see any more.
Okay. Thank you. Then we can move to the next talk.
Great. So our third speaker for this session, or our third paper, is going to be on adaptively secure constrained pseudorandom functions in the standard model by Alex Davidson, Suichi Katsumata, Ryo Nishimaki, Shota Yamada, and Takashi Yamakawa. And Takashi will be giving the talk. The floor is yours.
Can you see the screen?
Yep, I think we're good.
So thank you for introduction. So I'm Takashi. So I will talk about adaptively secure constrained pseudorandom function in the standard model. Okay. So constrained PRF, CPRF, is an extended version of the pseudorandom function. In CPRF, when we are given a key K and a constraint C, we can generate a constraint key denoted by K sub C, which can be used to evaluate the PRF on any input that satisfies the constraint C. On the other hand, even if we are given this constraint key, PRF values on input that doesn't satisfy the constraint remain pseudorandom. So this is the CPRF. So there are several flavors of security notion for CPRF, and especially we consider the following two axes of the security level of the CPRF. The first is selective security versus adaptive security. And the second is single key security versus collusion resistance. And ideally, the optimal notion of security notion of CPRF is adaptive and Q collusion resistance for all polynomial Q. So here I will review non-constructions of CPRF. And as a first category, we consider constructions from standard assumptions. There are many constructions in this category. However, we observe that all these constructions only achieve selective security, and most of them only achieve single key security. So our question for this category is, can we construct adaptively secure and collusion resistant CPRF for any functionality based on standard assumption in the standard model? And as another category, we also consider construction from obfuscation. In this category, One and Andre gave a construction of CPRF, collusion resistant CPRF for P/poly, which is the all polynomial size circuit. However, this construction is only selectively secure. On the other hand, there are two constructions of adaptively secure CPRF based on obfuscation. However, these constructions only support limited function class such as puncturing or NC1. So our question for this category is, can we construct adaptively secure and collusion resistant CPRF for P/poly based on obfuscation in the standard model? And in this paper, we give three new constructions of adaptively secure CPRF. Our first construction is adaptively secure and order-1 collusion-resistant CPLF for TC and F for any constant T from one-way function. Here, TC and F is the class of predicate that can be expressed as an AND of many clauses that depend at most T input bits. And especially this class includes bit fixing as a special case. And our second construction is adaptively single key secure CPLF for inner products from LWE. And our third construction is adaptively secure and order-1 collusion-resistant CPLF for P/Poly from indistinguishability obfuscation and LWE. And especially the first two constructions are the first construction of adaptively secure CPLF for any functionality based on standard assumption in the standard model. And our third construction is the first construction of adaptively secure CPLF for P/Poly in the standard model, even though we rely on very strong assumption of indistinguishability obfuscation. And there are several applications of our CPLF. So after uploading our first version of our work on ePrint, Tablery used our first construction to construct adaptively secure ABE for TC and F based on LWE. Unfortunately, her construction is not directly applicable to our second construction. On the other hand, and in our recent work, which will appear at Asia this year, we generalized her framework to be applicable to our second CPLF for inner product. As a result, we obtained the first construction of adaptively secure IPE from LWE, which has been open for almost a decade. And this is the summary of my talk. Thank you for your listening.
Great, thanks for the talk. So do we have any questions? If you have one, please post either in Zoom or on the Zulip. We'll give a few minutes for people to type in their questions. So I guess I can start with one. So any thoughts on extending or generalizing your techniques to get super constant collusion resistance? So trying to get, say, even logarithmic number of keys. Do you think there's any hope of getting such constructions from standard assumptions?
So I think our technique, okay, so we have three constructions, and for first construction, I think this construction, this construction is based on combinatorial technique, and I think the constant collusion resistance limitation is very inherent in this idea, so I don't think we can extend this to super constant one. And the second one is also only single key, and it is difficult to construct more than single key security. And third construction, it may be possible to achieve more than constant collusion resistance, but that is based on obfuscation.
Mm-hmm. I guess just a follow-up question regarding your third construction. So it looks like you require both indistinguishability, obfuscation, and LWE. So do you have any insight on what LWE is necessary for, and whether we can sort of remove that additional assumption and just reduce it to IO plus one-way function?
Mm-hmm. So we use LWE for constructing a primitive called shift hiding shiftable function. And here we try to construct that primitive based on IO and one-way function. But so as long as we can see, so that we require sub-exponential security of IO. So we think that it may be difficult to construct that primitive solely based on the polynomial hardness of IO and function.
Okay, cool. Thanks. So are there other questions?
No, I think that wraps it up for this paper.
Okay, great.
So we continue with our fourth paper for the session, which will be collusion-resistant watermarkable PRFs from standard assumptions.
Can you see my screen?
Yes.
Great. Thanks for the introduction. Today, I'm going to talk about how to construct collusion-resistant watermarkable secret functions from standard assumptions. This is based on a joint work with Manhou Ao, Zuo Xiayu, and Qiu Liangxu. So watermarking scheme can embed some information into a digital object without changing it too much. Also, it should be hard to remove the embedded information from the watermarked object without damaging it. In this talk, we focus on watermarking schemes for programs. Formally, it consists of a marking algorithm and an extraction algorithm. The marking algorithm can embed a message into a program with a marking key, and the extraction algorithm can extract the embedded message from a watermarked program with an extraction key. The main security property of a watermarking scheme is unremovability, which requires that the author is not able to remove or modify the embedded message from a watermarked program without significantly changing its functionality. Also, in practice, it is usually desired to have unremovability against collusion attacks. That is, the attacker may learn more than one watermarked programs, which are generated by embedding different messages into the same program. So one may hope to have watermarking schemes for arbitrary programs. However, as shown by Cohen et al. In 2016, we can't construct watermarking schemes for learnable functionalities. So in the study of watermarking, we usually focus on watermarking schemes for cryptographic programs, such as the declaration algorithm of an encryption scheme, the signing algorithm of a signature scheme, and the evaluation algorithm of a pseudo function. Now towards constructing watermarking schemes for cryptographic programs, we already know how to construct collusion-resistant watermarking schemes for public key primitives from standard assumptions such as the existence of one function, standard lattice assumptions, and so on. However, for watermarking schemes for pseudo functions, previous constructions from standard assumptions can only achieve a weaker single challenge unremovability, and the only known collusion-resistant watermarking schemes for pseudo functions are constructed from indistinguishability of execution. So the question is, can we construct collusion-resistant watermarkable pseudo functions from standard assumptions? So in this work, we solve this problem by providing a compiler that upgrades a single key circuit watermarkable pseudo function into a collusion-resistant one. The compiler only involves standard cryptographic primitives such as public key encryption schemes, signature schemes, fingerprint codes, and so on. All of them can be constructed from standard assumptions. By applying our compiler to previous constructions of single key circuit watermarkable pseudo functions from standard assumptions, we can obtain several standard assumption-based collusion-resistant watermarkable pseudo functions with various security properties. The new schemes can roughly preserve security of the original scheme, but our compiler will still comprise some properties of the underlying single key circuit watermarking schemes. First, the new scheme can only achieve unremovability against bounded extraction queries, even if the original scheme can achieve unremovability against unbounded extraction queries. Also, the new scheme can only support a polynomially large message space. It is an interesting open problem to remove these restrictions in the future constructions. So for some reason, I'm not able to explain why it is hard to construct collusion-resistant watermarkable pseudo functions from standard assumptions, and how we overcome these barriers in this short talk. Please see the long talk on YouTube or our full paper for more details. So that's all. Thanks for your attention, and I'm happy to answer your questions.
Thank you. Well, people are kind of coming up with questions. Maybe let me start. I was wondering, so did you look at any other secret key primitives? So did you try to apply your techniques beyond constrained PRFs? Or is there something that's inherent in your construction that these were kind of tied to the constrained PRF setting?
Okay, so our technique can be extended to other symmetric key primitives such as symmetric key encryption and message authentication code. But also, I think also, I think our technique can be extended to upgrade a single key secure watermarkable public key encryption into a collusion-resistant one. But we already know how to construct collusion-resistant public key encryption from standard assumptions. So we focus our technique on constructing collusion-resistant watermarkable pseudo functions.
I see. I see. And you mentioned that one of your building block components are fingerprinting codes. So I was curious, what are the constructions for those?
Sorry, you mean the construction of fingerprint code, or how we use it?
No. What are constructions for fingerprinting codes?
Oh yeah. Actually, in our construction, we need a fingerprint code. We need a fingerprint code with a stronger security property called security against extraction queries, and we give a new construction by adapting the well-known Bonnet shortcode to achieve this stronger security. So generally, the construction is similar to the Bonnet shortcode, but we adapt the decoding algorithm to improve its security.
I see. I see. Great. Thank you. Does the audience have any other questions?
So I have a quick question. So, so your work gives collusion-resistant watermarking for pseudo-random functions. Does your techniques apply in any way to get, say, collusion-resistant constrained PRFs? Since watermarkable PRFs and constrained PRFs seem to have similar functionality, so can we get any kind of collusion resistance for constrained PRFs through your frameworks?
Yeah, that's a good question. Actually, we can obtain collusion resistance, for example, puncture PRF by using our technique. But we can't get a standard collusion resistant puncturable pseudo function, and we have to restrict the puncture set to some specific form. And so I guess that is just what we needed in constructing collusion-resistant watermarkable pseudo function. But we can't get a general collusion-resistant punctural pseudo function. So we have to restrict the set the adversary can get for the constraint keys. I think they have to, for example, the adversary can only get one set, and then a set contains this set, something like that. So this is very restricted. So we focus on constructing watermarkable pseudo functions.
Great. I don't think we have any more questions. Thanks the speaker again.
Cool. So I guess let's move on to the fifth talk. So do we have a speaker for the fifth talk? Yeah.
All right.
I see Gianluca. Great. So our fifth talk in this session will be on non-malleable secret sharing against bounded joint tampering attacks in the plane model. This is work by Gianluca Bryan, Antonio Falmio, Maciej Obremski, Mark Simkin, and Daniele Venturi. And Gianluca will give the talk.
Thank you for the introduction. So in secret sharing, there is a dealer that has a secret message and wants to share it among other end parties so that only certain subset of parties are able to reconstruct the message. In particular, in standard secret sharing, there are two properties that are correctness, stating that all authorized subset of parties are able to reconstruct the secret, and privacy, stating that no unauthorized subset of parties should learn any information about the secret. In our paper, we also consider two additional standard properties that are leakage resilient and non-malleability. In particular, leakage resilience means that even if the attacker learns some information from possibly all the shares, still does not learn any information from the secret. And non-malleability states that even if the attacker modifies possibly all the shares and sees the reconstruction of the message from the modified shares, the new message is unrelated to the previous one, and thus the attacker still does not learn any information about the secret. And usually these two properties are considered together in what is called leakage-resilient non-malleability. In particular, in our paper, we focus on leakage-resilient non-malleable secret sharing against joint leakage and tampering attacks, and we consider two different models. In the first model, we consider the selective partitioning, that is, that the attacker commits to a single reconstruction set and a single partition of that set, and then he is able to jointly leak from and tamper with all the shares within each subset. In this setting, we prove that any one-time statistically non-malleable secret sharing scheme is also a leakage-resilient one-time non-malleable secret sharing scheme. And we prove this fact by complexity leveraging. In particular, we construct a reduction to simple non-malleability. And the reduction tries to guess the leakage. And finally, it checks that the leakage is correct using the tampering query. We also find two applications to this fact that are in lower bounds for the size of the shares of non-malleable secret sharing, and a construction of a compiler that takes as input a leakage-resilient one-time non-malleable secret sharing scheme and outputs a p-time non-malleable secret sharing scheme under in the computational setting. The second model we consider is the one of semi-adaptive partitioning. In adaptive partitioning, the attacker does not choose a reconstruction set and does not commit to a reconstruction set or a partition, but he is allowed to choose the partition for each query adaptively. However, in semi-adaptive partitioning, there is a reduction. That is that each subset of each leakage query is either inside or outside a subset of the tampering query. In particular, there should be no overlaps, partial overlaps between subset of the leakage partition and subsets of the tampering partition. In this setting, we construct a leakage-resilient secret sharing one-time non-malleable secret sharing scheme that achieves security against this kind of attacks. And our construction involves a non-malleable code that splits the secret in the left part and the right part. And then we apply a different leakage-resilient secret sharing scheme to each of the two parts. And finally, we pack each left share with the respective right share to obtain the final shares. The proof of security proceeds by hybrid argument, and actually we gradually proceed to separate the computation of the tampering query to the left part and to the right part, so that we can finally reduce to the non-malleability of the non-malleable code. Also, in this case, we have the application for the compiler for the p-time non-malleable secret sharing scheme in the computational setting. And finally, we leave some open problems. We are actually working on these open problems. We have a submission in TCC 2020. And the first open problem is to achieve continuous non-malleability rather than p-time non-malleability. And this kind of security against joint leakage and tampering attacks in the plain model. And the second open problem is to achieve optimal rate. We are actually able to improve the rate, but at the moment, optimal rate is still an open problem. And so that's everything, and thank you for the attention.
Great, thanks, Gianluca, for the talk. So it looks like we have one question from Zoom. So for other audience members, if you have additional questions, please feel free to ask in Zoom or on Azula. So the question from Subhadeep is, how much leakage can your scheme tolerate? It seems like it is possible to tolerate only logarithmic leakage, since you have to guess the leakage in the reduction.
Well, actually, since we choose the parameters ad hoc, we could choose ideally any leakage bound we want. We use bounded leakage, and so we can virtually fix any leakage bound we desire. because the underlying scheme, we can adjust the parameters of the underlying schemes accordingly. So if we need security, epsilon security for the leakage resilient one, non-malleable secret sharing scheme, then we adjust accordingly the underlying non-malleable secret sharing scheme with a particular parameter that is in particular epsilon over 2 to the L. So yeah, our constructions work in the under statistical security, achieve statistical security. So we can allow any leakage we want by adjusting the parameters accordingly.
Great. So any other questions?
I think that these were probably all the questions.
Great. So if not, then we can move on to the final talk in this section. Thanks again.
Okay, the final talk for this session is non-malleability against polynomial tampering.
Okay, thanks for the introduction. Can you see my slides?
Yes, yeah.
Okay, thank you. So the title of our work is Non-Malleability against Polynomial Tampering. And this is a joint work with Marshall Ball, Ishan Chattopadhyay, Tom Hawkin, and Liang Tan. So because of the time constraint, I will only give a brief summary of our main results. And if you are interested in the technical parts, please check our YouTube video or the paper. So first, let me tell you what is the non-malleable code. So non-malleable code is first introduced by Jampolsky, Piaczek, and Wicks, and it consists of a randomized encoding function and a deterministic decoding function. And we'll consider a tampering experiment, which we take a message S and encode it into a code word C. Then there will be an adversary who tampers the code word. Then we will decode the tampered code word to get a tampered message. And what we want to guarantee in this tampering experiment is two properties. So the first one is the correctness, which says if there's no tampering happens, then we should get exactly the original message. And second property says if some tampering happens, then either the tampered message remains unchanged, or it should become something unrelated to the original message S, which means it gets destroyed by this tampering experiment. So a simple observation here is it is impossible to construct a non-malleable code for an arbitrary tampering function. Otherwise, the adversary can just decode the code word and tamper it and re-encode it. So some restriction on this tampering function family is necessary. And in prior works, the most well-studied tampering function is probably the split-state model. But recently, some other works also started to explore the possibilities beyond this split-state model. And some examples are shown on the slides. So in this work, we consider the tampering functions to be polynomials over a prime field FQ. And formally, in our non-malleable code, the code word will be n elements over a prime field FQ. Then the adversary can choose some degree D polynomials as a tampering function. So if the adversary chooses like P1 to Pn, then the tempered code word will be P1x to Pnx. And our first result is we show that for every integer m and d and a sufficiently large prime q, we can construct a non-malleable code which encodes the m-bit message and is secure against degree D polynomial tamperings. And an interesting corollary of our first result is the same non-malleable code actually also works for arithmetic circuits. So an arithmetic circuit is a circuit where each gate computes either the sum or the product of its two inputs over some field. And if we consider tampering functions to be some size S arithmetic circuit, and it is not hard to see that a size S arithmetic circuit actually computes a degree 2 to S polynomials. So it directly implies that our non-malleable code also works for arithmetic circuits. So this is our first result. And our second result is non-malleable secret sharing. And thanks to Gianluca, we have already seen the definition of the secret sharing. And I just want to mention that in this work, we focus on T out of N secret sharing, where we can reconstruct the secret with T shares, but we cannot get any information about the secret if we only have less than T shares. And the recent work by Goyal and Kumar introduced the non-malleable secret sharing, which is basically a secret sharing with an additional non-malleability guarantees. And in this work, we show that for every integer m and dt and a sufficiently large prime q, we can construct a T out of n non-malleable secret sharing for an m-bit secret, which is secure against degree D polynomial tamperings. And furthermore, we actually provide a stronger security guarantee that we allow the adversary to adaptively choose the tampering functions. So more precisely, the adversary can first check some t-1 shares, and then use these shares to decide some degree D polynomials as a tampering function. And then the adversary will apply the polynomials on the shares to get the tempered shares. So we want to emphasize that this is actually a pretty strong security guarantee because it allows the adversary to tamper these t-1 shares like jointly and arbitrarily. So yeah, and similar to non-malleable code, our non-malleable secret sharing also works for arithmetic circuits. And to build these two results, the main building block of our two results is a C-less non-malleable extractor against polynomial tampering. But unfortunately, we don't have time to talk about this today. And then with this building block, we'll apply a reduction by Triachi and Goswami to get a non-malleable code. And then we'll apply another scheme by Lin et al. To get a non-malleable secret sharing. And in addition to apply these reductions, we actually need an efficient inverter for our non-malleable extractor. And this efficient inverter in our paper also contains some interesting new idea, which we believe might be of independent interest. Finally, let me show you some open problems. So the first one is trying to improve the parameters in our non-malleable code, such as the information rate and the error. And the second is to try to achieve non-malleability against polynomials over F2. And because our construction relies on whale bound, which is only non-trivial over a large field, so we think this might require some very different ideas. And finally, it will also be interesting to achieve non-malleability against some other tampering functions, especially those with some non-trivial average case lower bound, such as small width branching programs or AC0 circuits with parity gates. Thank you for your attention.
Thank you. So we already have some questions. So the first question is from Anna Kaplan. And the question is, can you go into more detail why you chose to look at polynomials over FQ for the tampering functions? Was the use in arithmetic circuits the motivation?
Yes, so the use in arithmetic circuit is part of the motivation, but I think, but I guess the main motivation is in some previous work. In the previous work by Chattopadhyay and Lee, they consider the affine functions to be the tampering function. So we want to try to generalize it a little bit more, like maybe consider the affine functions are degree 1 polynomials. Then we want to explore what we can do if the tampering functions are higher degree polynomials. So I think that's probably the main motivation of this work.
Great, thank you. The next question is from Mike Rosulek. What is the rate of your non-malleable code? How does it compare to other non-malleable codes?
So the rate of our non-malleable code is, so if we want to construct a non-malleable code which is secure against polynomials on n variables, then the rate of our non-malleable code will be 1 over n, where n is the number of the variables. I don't think we have a proper comparison between our non-malleable code and other non-malleable code because the tampering functions we are considering are different. So yeah, but in some other tampering function families, such as the split state model, they can achieve the constant rate non-malleable code in the 2 split state model, but I think it's incomparable because the tampering functions are different.
Okay, another question. from Shruti Sekar. Would you be able to get leakage from your non-malleable secret sharing? Also, what is its rate? So I guess, again, questions about rates.
Yes. So actually, the same secret sharing scheme is secure. So it is leakage resilient to affine leakage, but it is not really leakage resilient non-malleable to any kind of affine leakage. So to achieve the non-malleability, we allow certain kind of affine leakage, and some examples include like just revealing some of the shares to the adversary, like what we show in this adaptive choice slides. But there are certain kind of affine leakage which will break the non-malleability. So we don't want to include this as like part of our main result because it'll be weird to like prohibit certain kind of affine leakage. But it is non-malleable even if the adversary can get like some kind of affine leakage, I would say.
Thank you. Are there any other questions? Any follow-ups? Okay, I think since we have a few more minutes, I would open the floor to any questions for any of the speakers. If you forgot to ask a question for any of the previous speakers, also feel free.
Thank you.
I think this is a question again for the last speaker. Is this already implemented? Okay, I think we have more questions. You should stay on. So then we have a question from Evgeny. How complex is your encoding and deciding as a polynomial?
Okay, so okay, maybe let me share my slides again for the decoding for the construction.
Yeah.
So our our construction in this form. So based on the Triac-Goswami reduction, the decoding function will be the non-malleable extractor. And our non-malleable extractor is basically apply a polynomials on the input and then take the less n bit of the polynomial output as our output. And so this is the decoding function. It's pretty simple. And the encoding function will be an efficient inverter for this construction. And we achieve this by adapting a rejection sampling algorithm by Triac and Shokolahi to our settings. So and it's also not very hard. It's just like every time we choose a hyperplane and consider the intersection of it with the affine space, and then try to solve univariate polynomials. So it's also efficient.
Great, thank you. Any other questions for this speaker or any of the previous speakers as well? Okay, go. Okay, Evgeny has more follow-ups. How low is Q?
So this Q is polynomial in n, which is the number of variables, and d, which is the degree, and then 2 to the m, where m is the length of the message, and also polynomial in 1 over epsilon.
Thank you. Other questions? Going once, going twice. I think I don't see any other questions. David, do you have anything on your side?
I think we are set. I think all the questions have been addressed.
Great. Well, thanks everyone for attending this session and enjoy the rest of the conference.